So I'm going to start officially the topic of Boolean algebra, and this is the note which I'm going to share with you later on. But today I'm going to present this note because of one significant reason. The reason is that since we do not have much time, if I write the definition in the board and whiteboard, it takes some time. Okay, so I decided, and this particular thought came to me very late. Yet I have decided that to write it somewhere, to jot down the theorem statement and the definition somewhere, so that at least I can present. And what you can do, we can discuss the things in the whiteboard when it is required. So I think it would be a good option, and all of us will be agreeing to this particular decision. So the first definition of Boolean algebra, before I go to the discussion of Boolean algebra, let me talk about something about Boolean algebra, and you must know it, I think. So what happened in the year 1847, the basic laws of logic were described by the English mathematician and logician George Boole. Okay, and he wrote a very small book named The Mathematical Analysis of Logic. We have already done the logic and proposition in our class. So that time when he wrote the book, it was not, in discussion throughout. But later in 1854, he again published a research article on the laws of thought. And that gave birth to the so-called that we know about pure mathematics. So that laws of thought book is, you can say that this is the base on the basis of which this pure mathematics were evolved, various abstract structures were evolved on the basis of that particular research paper written by Boole. So in the name of Boole, the algebra that I'm going to study right now is named, and it is called Boolean algebra. It is by the mathematician named George Boole. Without further discussing the history of this Boolean algebra, let me get into the detail of this algebraic structure and let me find out what the definition is saying. It is something different, and we have already come to know various algebraic structures so far. We have studied group, we have studied ring, we have studied integral domain, we have studied field, and a long time ago when you were in first semester, you studied vector space, which is actually a linear algebra topic. So this is something else. It's another algebraic structure, and let me find out what this particular structure is saying. First of all, Boolean algebra requires one important item, which is a non-empty set, because you know that whenever we define the algebraic structure, we need a set. If I want to do some sort of algebra on the empty set, that doesn't have any meaning. So that doesn't bear any meaning. So we need to have some kind of elements on which we can apply something. So say, for example, if I now go to the classroom to take the physical class, when we know that in this particular situation, no students are present in the physical class, on whom I am going to rebuke it. Okay, there is no one to shout at the class. There is no one to do some mischievous things in the class. I'm not going to throw out anyone. I'm not going to throw out anyone out of the classroom. So for this reason, actually, personally, I am missing the students so much. I don't want to go to the college at all because students are not there. Okay, so that's how we want to do something, some sort of thing on some items, some elements. Here the elements are students, but students are not present. So the classrooms in the Techno India and in every college are now empty. School classrooms are empty. So there you can go to the classroom, you can start teaching on the blackboard, you can record your video, and then you can think that as if you are taking the class, as if the students are sitting, as if everything is going on smoothly. Okay, you can imagine just like a schizophrenic student person. Okay, but that is not the thing. We need something, some sort of a concrete set where elements are present. So every time when we define algebra, some sort of algebra, we need a non-empty set. So the first requirement of Boolean algebra, to define this algebraic structure, we need a non-empty set. And on this non-empty set, previously in group theory, we only defined one algebraic operation, that is addition, any sort of addition. In a ring theory and field and in integral domain, we defined an algebraic operation. We defined two algebraic operations on a non-empty set. Okay, in vector space, we defined two algebraic operations, one related to the set of vectors and another related to another set, which is called the set of fields. But here in Boolean algebra, we are going to define three algebraic operations on the set of, on the non-empty set that we have considered. One algebraic operation is called addition, another is called multiplication, another is called complementation. But here you see that I have chosen the symbol plus inside a circle and cross inside a circle. These two symbols will tell you, will remind you again and again that we are not dealing with ordinary addition or ordinary multiplication. We are dealing with something called addition and multiplication in its separate shape and structure depending upon the set whose elements are taken into consideration. So I have intentionally considered these two symbols, but we will call it addition and multiplication, no problem. Complementation, we have denoted this by C, or you can put a prime over here, just like we take the complement of a set. Okay. Now, after we get the non-empty set and we get the operations, three operations here have been taken into consideration, we have to define certain properties. First property that we are considering is as follows. Now, before I come to the property, the discussion of the property, first of all, that you are noticing probably that I have mentioned the word binary operation, and here I have mentioned the word unary operation. Okay, so why this is called binary operation? Because when we want to use these operators plus and cross, we need two elements. So these two operations plus and cross, they connect two elements, so we call it binary. And complement, to take the complement of a particular element, we need a single element, so we call it unary. Both binary and unary, by definition, they are closed. Every binary operation is closed, every unary operation is closed. So the closure property with respect to the non-empty set capital B is almost already satisfied. Now let us come to the property which is made in a serial order. The first property is called the commutativity. The commutativity property, and now this particular symbol, this cursor I'm showing, it is not prime, it is comma. Okay, so don't consider this to be a prime, it is comma. I have put a comma over here. So in commutativity, we have defined two things. First of all, with respect to the addition, the things must be commutative. A plus B must be equal to B plus A. With respect to multiplication, they also have to be commutative. No problem. Now, let us come to the second property. For all element A, B, C in the non-empty set B, distributive property will hold. Now, carefully observe that this distributive property, the second one I'm telling, that A into B plus C, if I read it like this, it is quite obvious. We know that this is a kind of distribution of the multiplication over the sum of two elements, isn't it? And we are very much familiar with this type of operation. A into B plus A into C. So we do not have any problem with the second one. But the first one is very atypical. This is the distribution of the addition over the multiplication. And this operation that I'm moving my cursor, you can see, this operation is very atypical because this doesn't happen in the set of numbers. So what is happening over here, you see, we write A plus B into A plus C. So you do not think of any set of numbers on which this happens. Okay, so this is very atypical and this is very typical. So these two properties are called the distributive law. One is the distribution of addition over the multiplication of two elements, and the second one is the distribution of multiplication over the addition of two elements. Next comes the property C, which talks about the existence of two elements. One is called 0 and another is called 1. These two elements are very distinct from one another because their jobs are very distinct. Okay, so first of all, the 0 element which is there, which we denote by 0, is what it is doing. It is, when added with the element small a, gives us small a back. Okay, so this 0 is called the additive identity. Second one, we are very much familiar with it. When we multiply a number with 1, then we get the number back. No problem. So the property C is typical property. But again, in property D, you will find the atypical nature of this particular set algebra. What is atypical nature? Carefully, if you think about the previous algebraic structures that we have studied, whenever we say that a plus 0 equal to a, then after that what it gives us the existence of 0 element. Then what we do, we try to find out the inverse, and we say that there exists some a complement or a prime for non-empty element, non-zero element a, for which a plus a prime equal to 0. But this is not happening over here. Actually, by looking into the property C, here we are supposed to get 0, isn't it? A plus a complement needs to be 0, but it is not happening. So it is very atypical. So here, instead we are getting this one in place of a plus a complement. And when we multiply the two things, okay, here I have used the symbol, prime. So let me rectify this particular thing. This should not be prime, this should be capital C, because I have used, or small c you can say. Okay, so whenever we multiply a with a complement, we get 0, and whenever we add a with a complement, we get 1. So that means the role of 0 and 1 are being interchanged with respect to the property D. Now, these are the 4 set of properties which needs to be satisfied with respect to the non-empty set capital B. No problem. You may be thinking that where is associativity hidden? Because we know that associativity kind of property which is always there. Okay, so it used to be there in the case of group theory, it used to be there in the case of ring theory, but here in this particular definition, associativity is not reflected. This is because associativity is not the inherent property. Associativity comes with respect to the properties which have been defined just now. Associativity will come with respect to a theorem later on. So it is not a part of definition, but associativity, it is quite obvious that associativity will hold over here. So you are not seeing associativity property over here because it will come later as a theorem, as a statement of a theorem. So with these simple properties, if these properties are satisfied, the mathematician or Professor George Boole, he said that, okay, if this is the thing, then I'm going to talk about some algebraic structure with a different name. And he has found this sort of structure. So what happened is that suddenly you do not come and tell me that, sir, I have defined a set, I have taken non-empty set, and I have defined this is operations, and this is my set. So it is a kind of different algebra. This doesn't happen in mathematics. In mathematics, what happens is that, first of all, you get an example. You try to dissect the example with respect to the known set of properties which you have around you. But when you are unable to dissect these particular practical example with respect to the existing properties, you need to develop a new theory, a new algebra, a new mathematics, a new analysis. That's how different structures are being evolved. But what in the classroom, when a teacher teaches a student with respect to a new algebraic structure, a new analysis, a new theory, the teacher tells the theory first and then showed the example. So while teaching, we just reverse the process. But while researching, the process is something different. Now, this obviously, I have already told you that this property C is called the complementation property, and AC will be called the complementary element of the element A. Now, in different books, Boolean algebra, the definition of Boolean algebra and postulates properties have been set in a different way. The property which I have used over here, these properties are due to Huntington, and these are called the Huntington's postulates for Boolean algebra. Boole actually didn't decide these algebras. Boole decided the laws of thought. He said that how to put a deductive argument to get into the details of some sort of structure. Now, later mathematicians modified it and they devised various algebraic structures. Huntington's actually gave this algebraic structure, and therefore this structure which I've shown just now, in case of Boolean algebra, is due to Huntington, and therefore these are called the Huntington's postulate. Now, once we have the non-empty set, once we have the algebraic structure, I mean the operations plus addition, multiplication, and complementation, and if these four properties are satisfied, then we call this 6 tuple. When there are inside parentheses, we write 2 element, we call it pair. When we inside parentheses, we write 3 element, we call triplet. When in the parentheses, we write 4 element, we call it quadruple. When inside the parentheses, we write more than 4 elements, we call give it, and suppose n elements are there, we call it n tuple. Here we call this as 6 tuple, because there are, to define this structure, we need 6 elements, basic elements: the non-empty set, the plus operation, the cross operation, the complementation, 0 and 1. 0 is the additive identity and 1 is the multiplicative identity. This structure is called the Boolean algebra due to the Huntington's postulate. Now, I'm going to stop the share and I'm going to move to the whiteboard to show you an example. The example is in front of you, it's exercise. I'm going to prove that this particular set that we are considering over here is actually a Boolean algebra. We are going to define a set, we are going to take a set which is non-empty, defined by capital X. Px is the power set of X, set of all subsets of X. In case of plus, we are going to take union. In case of cross, we are going to take intersection. And complementation is also defined over the elements of Px. So the question is Px a Boolean algebra with respect to these operations? I think it would be it would be wise if I do this short mathematics in this page, so that the question remains in front of you and you can otherwise I have to open the this particular presentation and whiteboard again and again. So let me try to do this example here in this particular sheet. Now you see that union operation, in place of plus we have the operation union, and in place of cross we have the operation intersection. And obviously this union operation and this intersection operation, they are actually binary operations. Okay, so if we consider 2 elements from the set Px, and if you take the union of these 2 elements, this is another set, obviously. So, and complementation, and therefore we can at least say that if A and B is belonging to the set Px, then we will define A plus B by A union B and A cross B by A intersection B. And we will define A complement by the definition X complement A. Okay, so these are the operations which have been defined. I am going to check the properties one after another, one by one. First of all, let us come to the property which is called the commutativity property. So in commutativity property number 1 is that you know that for all A and B belonging to Px, yeah, you can write your roll numbers in the chat box. So for all A, B belonging to Px, A union B and B union A, they are same thing. Not only this, A intersection B and B intersection A are also same. So commutativity property hold, no problem. Now second comes the distributive property. Now, distributive property, remember that A plus B is A union B and A cross B is A intersection B. The distributive property, as you know, what the typical distributive property was like this: A cross B into B plus C. A cross B plus C means A cross B plus A cross C. So I'm going to prove this first of all. Now, in place of cross, I'm going to take, first of all, let me consider three sets for all ABC belonging to PX. So first of all, I'm going to consider A, and in place of cross, I'm going to consider the intersection sign. So A intersection B, and in case of plus, we are going to consider the union sign. So A intersection B union C. And by the distributive property of set theory, this can be written as A intersection B union A intersection C. So now you can compare this result with the given one, and you see the distributive property of intersection over the union of two sets are actually holding. Second atypical distributive property is this one: the distribution of plus over the distribution of cross. So we can write this atypical property as A cross A plus B cross A plus C. This is very atypical, and it cannot be true for the set of numbers. But in the set of in this particular set PX, it is going to hold. So you consider A, the set A, you consider union in place of plus, and A union B intersection C. If I write, then by the distributive nature of set theory, we can write it as A union B intersection A union C. So you see these two properties, this is called the distribution of union over the intersection of two sets. So you see that this particular property is atypical property is getting hold over here. Second, we need the existence of identity and existence of two identities. One is the additive identity, another is the multiplicative identity. So what we need to do, we know that the null set, if I consider this to be the null set phi, this belongs to PX, isn't it? Because phi is the subset of all X, since phi is subset of capital X. Now, for all A belonging to PX, we know that A union phi is equal to A. What was my existence of identity? A plus 0 must be equal to A. So we are getting this. Also, we see that whenever since capital X also belongs to PX. Okay, so A intersection capital X is equal to A. So in place of 0, here in this example, in place of 0, we are getting phi. In place of 1, we are getting X. So phi is playing the role of additive identity, X is playing the role of multiplicative identity. So in this example, phi is the additive identity, X is the multiplicative identity. Since you are going to sit for the online examination, you may be thinking that what sort of question is asked in this, will be asked or can be asked in the examination. So I can set an example, I can set a question like this. So if this is the example, what is the multiplicative identity and what is the additive identity? I can give you several options, but from where you are going to choose. So we have shown that the property 3 is being satisfied. Next comes the property of complementation. Now let me use a different color because everything is getting mixed up over here. So in property D, now you see that we need A plus A complement equal to 1. So if I consider the set A and you take the union of A with its complement, which we denote by AC. So A complement, A union A complement doesn't give you phi, it gives you X, isn't it? So you can see that this particular thing is being satisfied over here. And if I consider the intersection of A with A complement, we are actually getting phi. So this is also being satisfied over here. So with respect to the set considered and with respect to all the operations, Everything is, all the properties that I have mentioned in the definition are being satisfied, and therefore we can say that this set Px under the operation, these two operations, they are, this is a Boolean algebra. Or rather, if I stick to the, if I like to stick to the notation, I can write it in the following way, that the set Px with union and intersection and phi and x, this 6 tuple is a Boolean algebra, is called a Boolean algebra. Okay, so I think you have understood that how to show this particular set of axioms on a particular set, non-empty set, and how it becomes a Boolean algebra. Probably you have understood, and probably you have copied the things also. So I'm going to move on to the next topic, which follows. So just a minute, because I have to erase this. So next comes a theorem. Now in this theorem, you see several statements have been made. We have considered a Boolean algebra of this form. Okay, let me save your chat first of all, otherwise I'll forget. Okay, so we have considered this Boolean algebra with the given operations, and we are going to show a few properties. First of all, we are going to show that the elements 0 and 1, that the additive identity and multiplicative identity, they are unique. Now, if a small a is the element of B, then it has a unique complement, because it means that there cannot be two complementary element for a single element. And some other properties are there. For each element a complement of complement will be same, this one. 0 complement will be 1, 1 complement will be 0. And these are the two properties which are very important. One of the properties is idempotent property. You have seen this property before in the group theory. It satisfies, we can get an idempotent element in case of the set of matrices. This property is there. And there is one important property which is called the absorption property. So absorption property is given as this. See, actually, what happens in if I write the distributive property A cross B plus C, what do we get? By distributive property, we get A cross B plus A cross C, which is very atypical, you know. But what it is written over here, if two of the elements, they are same, so the resultant element will be the element A, which is getting repeated over here. So the element B is getting absorbed inside it somewhere, and it doesn't actually have any effect on the output. Similar is the case over here. You are going to distribute plus on the multiplication, but two of the elements, they are same. Then the element which is not being repeated, it is getting absorbed somewhere and doesn't have any effect on the output. And therefore this property is called absorption property. Why these properties are actually important? Because the fundamental usage of these properties is to build gates, different gates in algorithms like NAND gate, OR gate, XOR gate, different gates. To use gates to derive gates, we actually use this Boolean algebra very much. And it's not only in classical computation, but in quantum computation also, we are actually, this particular algebra is very useful in quantum computing. Nowadays, this quantum computing is a very evolving science, you know. And you have this quantum computing in your 7th semester course as an optional paper. So if you take this particular optional paper, you can get help from me, okay? Because my PhD was in quantum information science. Now, anyways, so in these properties can be easily proved, and now as you have already understood that this particular operations plus and cross, they actually mean what? So right now, for the sake of doing problems, instead of writing A plus B like this, I'm going to write it as A plus B. Just do not think that this plus is the ordinary addition. In place of writing A cross B like this, I'm going to write it as AB only. Don't think that it is ordinary multiplication. I'm going to do it just for the sake of simplicity. So how can I prove these properties? So let me show one after another. So first of all, let us talk about this zero element, isn't it? Let us talk about zero element. Let us show that this zero element is unique. If possible, there are two zero elements. 0, 1 and 0, 2 are the zero elements of this Boolean algebra. Okay, and which should not be. Now, if it is so, then for all A belonging to B, A plus 0, 1 is equal to A, and A plus 0, 2, that is also equal to A, because both 0, 1 and 0, 2 are playing the role of zero element. Now, since it is true for every A, so what we can write that 0, 1 is an element, is an element of capital B, and 0, 2 is also an element of capital B, isn't it? Both of them are elements, so this result is going to hold for 0, 1 and 0, 2 as well. So we can write it, from there we can write 0, 1 plus 0, 2 is equal to 0, 1. I am treating in place of A, I have considered 0, 1. And here in place of A, I am going to consider 0, 2. So I'm going to write 0, 2 plus 0, 1 equal to 0, 2. This means that in this case, we are treating these two elements, this element 0, 1 as my A. And here I'm considering these elements 0, 2 as my A. Okay. And here I'm considering this as the identity. And here I'm considering this as my identity. If you are confused, that's why I'm writing it, showing you. Now you see that since plus is commutative, I can write 0, 2 plus 0, 1 as 0, 1 plus 0, 2, which is equal to 0, 2. Now, if I give it equation number 1, and if I give it equation number 2, from 1 and 2, what I can say? From 1 and 2, since the left-hand sides are same, right-hand side must be equal to same. So 0, 1 equal to 0, 2. And 0, 1 is the additive identity according to my choice. 0, 2 is the additive identity according to my choice. They are coming out as similar. And therefore, 0, 1, 0 element is actually unique. Now, how to show that the element 1 is unique? For this, I can do something which is actually, we didn't do it in case of other algebraic structures. For this, if you want to do it easily, you can take the help of a duality principle. So what is this duality principle? I have not mentioned the duality principle in the note, but intentionally, but after this class, I will add it somewhere. Duality principle means, remember that you already know that proposition. What do we mean by proposition? Proposition is something, some statement or some sort of algebraic identity that we are actually working with in case of some algebraic structure. So if I state something about the algebraic structure, that becomes your proposition. If I add some properties, that becomes your proposition. Now by the dual of a proposition, let me write it over here. By the dual of a proposition, capital A, in a Boolean algebra, we mean the proposition obtained from A by replacing plus with dot, or by replacing dot with star with plus, or by replacing 1 with 0 or 0 with 1. Okay, and it is also true that if a proposition A is derivable from the axiom of a Boolean algebra, its dual proposition is also derivable from these axioms. I'm again repeating, if a particular proposition is derivable from Boolean algebra, its dual proposition can also be derivable from the principles of the Boolean algebra. I shall make this particular point in the, I shall introduce this particular duality principle inside my note. I'm still preparing my note. It is not complete. That's why I have not introduced it over here. So since 1 is the dual for 0, you know that 1 is the dual for 0 and 0 is the dual for 1. So if I am going to replace 0 by 1, and if I do the similar calculation, I can easily predict that it is going to hold for 1 also. Because by duality principle, we know that if one particular principle is derivable with the principles of Boolean algebra, its dual can also be derivable with the same principles of the Boolean algebra. And therefore, since we have already shown that 0, 1, 0 is the unique additive identity, and since 1 is the dual of 0, since we have shown that 0 is the unique identity of B, and since 1 is the dual of 0, by duality principle, it can be easily shown that 1 is the unique identity also. Okay, so you don't have to do this rigorous calculation that I have done over here. You don't have to repeat this calculation again. You can directly conclude from your duality principle that it is also being happened for 1 as it happened for 0. Since I have less than 1 minute time, so I'm going to stop over here. We are going to continue in the next session.